Hey everybody, it's my privilege today to introduce Jack to you. Jack Holt is a professor here in the Department of Geosciences as well as in planetary science. And we snagged him in 2018 to be the director of our brand new and completely awesome Earth Dynamics Observatory, as well as an awesome professor. And the goal there was to combine the university's strengths in space exploration, instrumentation, and earth sciences to learn more about our planet and maybe, come up with some bucks while he was at it. And since I'm PIing one of the missions that are being sponsored by the Earth Dynamics Observatory, I'm a huge fan, not least of which because Jack is actually an amazing ice guy. And when I say ice guy, I mean not just on planet Earth, he's also ice on Mars. So debris-covered glaciers on Earth and Mars, terrestrial glaciers and ice sheets, as well as Mars polar studies and some volcanic flows, features, and processes. We were really lucky to get him from UTIG. Although apparently we've been, raiding their cupboards regularly now, so that's outstanding. But he also teaches like a really cool class on radar remote sensing of planetary surfaces, which sounds like he actually just put a bunch of grad students to work for him. I'm not entirely convinced that's not what he did. But here he got his undergrad degree from Rice. He got his master's and his PhD from Caltech. He has been a postdoc scholar at JPL. We are super lucky to have him. And I just want you to know that he's really terrible with acronyms. His lab is Terrestrial and Planetary Investigations with Radar, which is TAPIR. Who the heck names their lab TAPIR when they work on ice and debris flows? And the coolest thing is my son had a real terrifying experience flying with Wright Flight when he won this this extra two-man plane experience, and the ailerons went out. And Jack, when my son walked up to him and told him about this, because he knew Jack was a pilot, he says, "Jack, blah, 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 blah." And instead of saying, "Oh, that's no big deal," Jack looked at him and said, "That's really serious. You're lucky to be alive." At which point my son was like, "Yeah, woohoo." He wants to be a pilot too, Jack. You're inspiring people all over. So he's had a serious impact both on Mars and on Earth. And he's going to tell us today about Alaskan glaciers. And I just want to point out, and also on our UA community here, building something like Earth Dynamics Observatory is, I imagine, can be a pretty thankless task to try and help other people win with their research. And so I'm so delighted to have Jack here with us. And also, we can always use more ice people. So especially one as clever. I mean, I actually was looking at his instruments, like the long wavelength radar echo sounder, again with the acronyms low res, and then very efficient radar, very efficient team, Vervet, which is the predecessor to low res, and then Rock Glacier Pod Racer. These are so cool. I can't wait to hear more about what you're up to. Well, it looks like you're going to talk about on planet Earth today, so awesome. Although Mars is also cool. So thank you, and welcome, Jack.
Well, thank you very much, Joellen. That was really nice introduction, and I appreciate it very much. And it was super fun talking to your son about his experience, because nothing like that has happened to me flying. And I'm really happy to be here. It's a really, really fun being part of Geosciences at UA and LPL. It's a great community. I'm having a blast. And those acronyms were mostly made up by my former student and current research specialist, Michael Christofferson, who's one of the people I would like to acknowledge here at the outset of this talk, along with Brandon Tober, who's a PhD student in geosciences here at UA, and he just passed his oral quals this morning. So congratulations, Brandon. I hope you're drinking a beer. You also just drink a beer right now anyway. And then Chris Larson and Martin Trufer, who are colleagues at University of Alaska Fairbanks. This photo is of our main survey plane for Alaska. sitting on top of the Bagley ice field or ice valley, which is a massive chunk of ice sitting, you know, in a non-polar setting. And it's been described as, and I think this is right, the third largest ice mass in the world, or ice field after Antarctica and Greenland. It's this. So yeah, I've done a lot of work on Mars, Antarctica, some other things. I've been working in Alaska for the last 4 or 5 years, and I haven't really given a lot of talks on this aspect of it. So there's some new stuff in here. It's kind of a work in progress for sure, but I'm really excited about it. It's a lot of fun, and I hope to convey a little bit of that motivation for it to you today and help you learn a little something about Alaska. So, uh-oh, my arrow is not working. Why is it not working?
Jack, you should just click in there. I think it'll work. Yeah, try
Clutter.
now.
That worked.
Yep.
Try to find my mouse. Okay, so this is our field area. It's pretty big. Basically, all the white in there are glaciers in Alaska that we try to map in this program. I'm not going to be talking about all of them, but there's been a long-standing program at University of Alaska Fairbanks to monitor glaciers. And so we basically try to hit all of that. Not every year, but over a few year period. I'll get back to that part of it. So it also extends into Canada over here. This corner, we fly over the glaciers and don't land, but it's a big area to cover. I'll be mentioning mass balance a bunch, and if you're not familiar with that, a mass balance of glaciers basically means just, is it gaining or losing mass? So you've got an accumulation zone where it's mostly usually snowfall, adding mass to the glacier, and then below an equilibrium line, you've got an ablation zone. And you're losing mass mainly due to melting and calving. And so if you have a positive mass balance, the glacier is growing. If it's zero, it's in steady state balance. If it's negative, it's shrinking. So looking at Alaska, it's pretty amazing. It's looking worldwide. So if you don't include Antarctica and Greenland, Alaska beats out everywhere else in terms of glacier contribution to sea level rise. So this is a compilation from 2013 from Alex Gardner and others, looking at all of these regions with glaciers. And the circles here represent, the red part is the mass budget. So red is negative, and then the outer circle is the area that's glaciated. So in both categories, Alaska is pretty big and the ratio is big. And over in this table, Alaska is the top of the list, at losing it about, in this publication, about minus 50 gigatons, or losing about 50 gigatons per year, which is quite a lot. Another way to look at it, this is some of the results of that long-standing program at UAF to monitor glaciers with airborne laser altimetry. And you can see this map is mostly red, and that's in the negative part of the mass balance. There are a couple areas that are blue. There's one in the middle here. Hopefully you can see my mouse, my cursor, but that's the Hubbard Glacier, which I'll bring up later in the talk. It has a huge catchment area, one of the largest ratios of accumulation area to ablation area of any glacier. And so it's actually pretty healthy, but everything else is in the red, losing ice fast. And so based on these measurements, Larson and others estimated about 75 gigatons per year of loss, which is equivalent to 0.2 millimeters per year sea level rise. So every 5 years, another millimeter added to the ocean, so it's sea level. But the interesting result was that tidewater glaciers that empty into the ocean and calve, contribute only about 6% of that loss. It's mainly surface melt across many, many glaciers, and most of them land terminating or terminating into lakes. So elevation change from laser altimetry is certainly a good way to get at mass balance for individual glaciers, but you have to make assumptions about, lots of assumptions, because you're basically combining accumulation and ablation when you do this. And there's a plot of Grand Plateau Glacier, from publication and prep, showing on the left side here, you see the big negative change in elevation up to 10 meters of drop in elevation per year. That's at the lower elevations, so that's in the ablation zone. And then up in the accumulation area, it's pretty close to zero. And so it's not the accumulation that's falling off, it's the increase in the ablation. And this is a common theme across all of Alaska. You can also measure this regionally with gravity, and this is from Grace and Grace Follow-On by Chris Herrig and Simons, Frederick Simons, I guess. And then so if you look at the mass change in the whole region, you can get this wiggly plot over here, and you get a big seasonal cycle in mass going up and down, and that's 2 to 3 times as large as the seasonal cycle in Greenland. And then this downward slope over time is the average ice loss. And if you combine these two areas, they split it up, and it's about 40 gigatons per year. So there's certainly some variation in estimates of loss. They're all negative and they're all big. So the motivation for our work has been to study these things while we can. They're changing very fast. There's rapid retreat nearly everywhere. There's proglacial lakes forming on many of these glaciers. This picture on the right is looking downstream from the terminus of Tana Glacier. And this lake is formed in just the past few years. It's just full of chunks of the glacier falling apart into this lake. And then of course they melts fast once it's in there. The presence of a proglacial lake at the terminus really increases the amount of ablation. And then this is a pretty picture from the lake at the end of Bering Glacier, which is just enormous. And it's growing rapidly too. A bunch of icebergs in there. We call it the iceberg graveyard because they mostly don't make it out to the ocean. And there's very few constraints on the ice thickness and the bed topography. And you really need that. You need to understand the whole glacier in order to predict the geometry of the glacier, to predict how it's going to retreat and how it's going to react to climate change, especially for these big glacier systems that I'll be talking about. And there's also a few constraints on accumulation. That input part of the mass balance equation, we don't have a lot of good ground truth on that, and the satellite observations aren't very good in that region. And we need that to better measure mass balance and to assess the regional climate processes that are at work affecting these glaciers. But I'm going to be focusing mostly on pretty much all of this is about ice thickness and bed topography. So most of this work that I'm describing has been done under the umbrella of Operation Icebridge Alaska, which is a NASA program that was meant to fill a gap when ISAT died and they had to build a new ISAT. And so I think it's been going about 10 years, maybe 8 to 10. It's been the main goal for Operation Icebridge Alaska has been to continue the LiDAR measurements they were already doing, and with the scanning LiDAR, and then about 5 years ago, Chris Larson asked me if I could help out with ice thickness and bed topography by adding radar sounding. This is the plane we mostly use. We've added another small Cessna now to do LiDAR as well. We actually had both operating this past summer. This is a turbine otter on skis. So basically you can go anywhere with this thing. We sometimes land up on a glacier to refuel from drums. This is the scanner. It's pretty compact. It sits in the back of the plane, looks through a hole. And I'll talk about the radar in a little bit here. These are the glaciers that we have flown, and most of these have been repeated multiple times over the years. And it's pretty challenging to get around and get these things. We mostly operate out of this lodge where the owner of the plane is based right here in the middle, and we can fly to basically do a round trip to any of these glaciers in one day, although it's not super efficient. So sometimes we'll relocate for a few days. And the lodge it's kind of cool because it's in the middle of nowhere. It's surrounded by Wrangell St. Elias National Forest. There's a picture on the left. It sits next to the Chitna River. You can only get there by airplane. That's about 1,000 feet long runway right there. And so there's typically an array of cool bush plains out next to the runway. It's a beautiful spot, but the facilities are kind of limited. So here's Michael working on the radar out on a mobile workbench out here on the runway. And that's fine when the weather's great. And then we often we eat pretty well there. It depends on what's going on at the lodge, but we often have free range, organic, local food that's been prepared for us in an interesting way. What else? Oh, on days off, basically when the weather is not good for getting out over the glaciers, because we need cloud-free, it has to be cloud-free over the glaciers to do the laser mapping. We'll maybe hop in our planes and head out to the coast and do some beach combing, check out shipwrecks. And I don't do much fish. I haven't had time to do much fishing up there, but every once in a while somebody catches some fish, and then we might end up cleaning fish while debugging radar stuff. But most of the time we're out flying, doing surveys or checking weather. This is a little GoPro time-lapse video of a flight over a glacier this past summer, just to give you an idea what it's like. This is in the St. Elias Range, kind of southeast Alaska. Steep stuff. Like we're going from about 13,000 feet up here, and the glacier drops down to sea level in a very short time. So the camera is mounted on the wingtip, so the banks and are a little bit, the maneuvering is a little bit exaggerated, but this is kind of what it looks like on a good day. Pretty spot. So what I've been focusing on is ice thickness and bed topography, and the way to do that is to use radar sounding. In general, long wavelengths, so meaning like a meter or more, generally penetrates freshwater ice quite well. This is below there. This is a plane we've used in Antarctica in the past, or I've been involved with 60 megahertz antennas, so that's 5 meters wavelength. And you can see through 3 kilometers of ice, no problem in Antarctica. It's really cold ice, which helps reduce attenuation. And you just go along and you fire out these pulses and you record the resulting waveforms. And this is a plot of just on the right side of this is just a single trace of power with this big surface echo, and then dropping off reflections from internal layering, and then a bed echo down here at the bottom. And as you fly along, you just build up this cross-sectional profile. Well, that's all. It's actually quite easy in Antarctica because in most places it's really flat, and like I said, the ice is very cold, and so getting through 3 kilometers of ice is not a big deal. Alaska is a totally different story. It's warm, it's wet, it's highly crevassed. There's debris everywhere. There's topography everywhere. We weren't even sure it would work. It hadn't really been done much when we started trying this. So we went to very long wavelengths. And by long, I mean 60 to 150 meters. And you have to basically tow a wire antenna behind the airplane. And there's been a series of radars used in Alaska, starting with one built by JPL here called WISE, one that UAF built, one we built at UT, and then now one we've built at Arizona. And so the one we built at Arizona, I'm not going to dive into all these details, but it's a very flexible, capable radar, and you can operate it at whatever frequency you want. We have antennas for 2.5 and 5 megahertz. You can chirp it. You can change the pulse duration, the pulse repetition frequency. It has 2 kilowatts of transmit power. It's a really slick system. The biggest challenge probably is surface clutter. When you are flying through these valleys, and this is Logan Glacier, which is actually not that, it's up valley from the lodge where I was showing you the pictures of where we base out of. There's a lot of topography there, right? And so if you've got a radar flying over the surface, this is my super high-tech drawing. Hope you like it. the radar is you're sending a signal down to, and you get an echo off the surface. And then if you're lucky, you get signal going through the glacier to the bed and you get an echo back. But since it's a towed wire, you get this big like donut shaped antenna pattern that's just sending energy basically everywhere. So you get echoes off the walls as well. So it's actually can be a big mess and hard to interpret. So what we have to do is predict the clutter, which are these surface echoes from the sides, using topography and the flight path and a model of the radar. It's basically a simple geometrical optics model. So here on the left, you got the imagery, the flight path down the glacier, starting on the right here at the green dot, doing a little turn to get on the course, and then going down the glacier. On the right is the digital elevation model, and then I'm going to show you the radar data from that. And you don't really see the surface echo, it's buried up here in the outgoing signal at the top. But then you see what a lot of people would interpret as the bed, because you're starting over here on the left, up on the glacier, you're going down towards the terminus. You get this kind of nice, dark, this strong return that's getting thinner and thin. You know, the ice is, if it's ice, it's getting thinner and thinner. It totally looks like a bed echo. But you do the clutter simulation, guess what you see? It's pretty much the same thing. So I'll flip back and forth. The clutter simulation, this is all simulated from the surface. So anything that shows up here in the radar data, shows up like this, is from the surface. So just flip back and forth, and the bed, the putative bed echo is pretty clearly just cluttered. So there's really nothing you can do here. You can't interpret a bed. There's one from Bering Glacier, which is an easier one to deal with, because this is a really broad, wide glacier, several times wider than Logan. So on the top, you see the radar data, a nice return here, and then down in the clutter simulation, there's nothing. So the clutter is way down far away from those echoes. So in this case, we can confidently say, this is the bed echo, and here it's getting down to, or up to about 850 meters of ice thickness up here in the central trunk, which puts it below sea level. This is a big, deep glacier. I'm not going to talk any more about Bering, but it's an interesting one. All right, so that's that. Hope that made sense. Just showed you some data from Bering. I'm going to jump around a little bit. We're going to talk about Kennicott Glacier, and then Hubbard Glacier, and then Malaspina Glacier. Kennicott. I like Kennicott. It's pretty cool because it's right next to McCarthy. McCarthy is a little town. If you've ever seen the reality TV show Edge of Alaska, that's where it's based. And I'd say the TV show is pretty ridiculous, but there are a lot of characters there. Like it's a weird place. So to give you a sense of scale here, since I didn't put scale bars, sorry. When you zoom in to the terminus, there's the McCarthy Airport. That is, I guarantee you, that's not a big airport. The runway there's maybe half a mile long, 2,500 feet or so. So that's a big glacier. Let's leave it at that. Here's a view looking down towards McCarthy on the left. Huge ridges. These ridges are up to like 50 meters high of medial moraines converging, lots of debris. This is the Crow Glacial Lake that's growing. There's a few houses you can see here on the edge. It's growing fast, and the residents are pretty worried what's going to happen as this glacier. I mean, it's been retreating a lot. So we flew a couple lines on that. We've actually flown quite a few, but here's one example from our 5 megahertz system, starting over here at the green triangle, going up and then back down. And you can see these returns right in here that do not all show up in the clutter simulation. Now, some of them do, like this little sort of hyperbolic looking thing here is probably clutter. Same over here, but this part is not. And so I'm going to plot just what we've interpreted as bed based on radar profiles going up glacier. or the plot goes left to right down Glacier towards the terminus. And you can see the lake level here on the right, down at the terminus. And if you go inward, it drops off quite a bit, almost 100 meters, and that's a large area. This is potentially a future lake. Like if that keeps expanding, that's a large area. It's going to be a big lake. And then if it gets past that, this ridge will probably buttress the glacier, but there's a massive over deepening past that. So a very deep erosional basin below that. So that indicates instability, basically. Once this thing gets going, it could retreat quite fast. So Hubbard, so go back to Hubbard. I mentioned it has a very large accumulation area. It actually goes all the way up here somewhere to Mount Logan, which is in Canada. Hard to see on this picture, but Logan is huge. And we'll zoom in on Hubbard. It's the largest non-polar tidewater glacier. So some qualifications there, but it's another massive tidewater glacier. And it's kind of bizarre because it hasn't been retreating due to this huge catchment area. And sometimes it even advances. In 2002, actually, it advanced and closed off this gap over here. I'm going to show you a couple of photos of that. So this is Russell Fjord. Hubbard Glacier comes down into this bay. And if it advances enough to close this gap, which you can see right over here, looking over at the terminus of Hubbard, it can basically, water will build up back here in Russell Fjord until the point where it eventually breaks the ice dam and it makes a big flood that comes down here. And the town of Yakutat is down here, and they're not too, excited about that idea because it's happened a few times, and it could happen in a bigger way. And then the Army Corps of Engineers has been worried about it could back up. The water could actually go over these forelands down here to the ocean because that's low topography, and it could wipe out the Seatook River salmon fishery, which is kind of a big deal. So people are interested in trying to understand how Hubbard Glacier works and if we could predict advanced scenarios. So we started collecting data over Hubbard. Here's an example. It's super crevasse. Let's go back to this picture really quick. Like this is flying low over the terminus. These are just, I mean, you could swallow the plane if you went down inside one of those things. But the radar works through it. Here's a bed return. Here you can see nothing in the clutter out here in the middle of the glacier terminus. This is a profile then going in from the terminus down to the higher on the lobe down to the edge of the terminus, and you can see it's very thick. It goes to like 400 meters below sea level right in this region. So that's super interesting and deeper than anybody really expected. Just a quick little call out to Michael Christopherson's work here. He took all the data we had, including data was flown with this JPL radar, which had a lot of issues, and we had to repick it and do the clutter analysis because they didn't do that. But he combined everything we had, and it looked pretty good. And after all the corrections to the JPL data, we had pretty good crossover agreement within 30 meters in those places, which is getting close to the theoretical resolution of the radar. And actually, yeah, about is at 2.5 megahertz. So then he wanted to do even better than that and applied this mass conserving bed method. So you basically assume that the mass going through any volume goes in and goes back out, and you use the surface mass balance, the velocity, and ice thickness to constrain the bed. Well, the ice thickness at the points where you measure it, but in between you don't have it. So you have a free parameter, which is the ice thickness or the bed elevation. And so these are the flow paths that he did this calculation for over on the left. And he got data from various sources, satellite data for surface velocity, surface mass balance from nearby studies on the ground, and then time series of surface elevation from the repeat LiDAR flights that we had. And then he came, so that resulted in this map on the right, which is a pretty nice map combining all this information. And so the interesting things are, well, first of all, it's the first map of the Hubbard terminal lobe that anybody's ever made. It's well below sea level and under the lobe. There's a kind of a bedrock ridge up here, and then there's a low area behind it that's even below sea level. And then the deepest trough is not in the center of Hubbard, like right at the mouth, like coming out of the center. It's at the convergence of this glacier over here, Valerie Glacier and Hubbard, which is interesting and kind of unexpected because Hubbard is a much larger area, glacier with a lot more flux of ice than Valerie. So you'd think it would just dominate the erosional processes there. So that's Hubbard. That's totally new. And now Malaspina. Malaspina, you can, I mean, it's we're going to zoom in on this next, but it looks different, right? It's like a big pancake with tiger stripes. It's what's called a Piedmont Glacier. It flows out from the mountains, and actually a few of them here that combine into this one big Piedmont, and it is the world's largest Piedmont glacier. So it just basically flows out into this flat area and just spreads out, and then yeah. So we're embarking on a whole new study of this, and I'm going to show you mostly results that Brandon Tober put together recently, and he presented some of this at his orals this morning. So I want to make sure to give him credit for that. So just to give you an idea for a better sense of the size of this thing, you're probably familiar with the Tucson Basin, right? There it is, sitting there. If you plot Malaspina down at the same scale, that's what it looks like. So I'll just flip that back and forth. So it would more than adequately fill in the entire Tucson Basin. Here it is, semi-transparent, overlaid. The main lobe here would fill the entire Tucson Basin and go south, and then this Agassiz Glacier up here would take out Marana. Of course, the whole thing would probably melt a little faster if it was here in Tucson, but we'd be sitting under several hundred meters of ice. Okay, so why are we interested in it? Why do we care? It's showing signs of potential collapse, and it occupies a big chunk of coastline. It's a lot of ice. The OIB surface elevation measurements are showing up to 10 meters per year. 10 meters per year, which is a lot of thinning along the outer parts here of Malaspina. And this little thin strip of coast that separates the glacier from the ocean is totally falling apart. It's showing all these signs of thermokarst, which indicate, these pits are basically when ice starts melting and then you get this runaway effect and they grow. And you can see trees falling into those edges. There's also these little lakes that are marching their way and growing in. We call this one the Lagoon of Doom, because we actually noticed over the years this thing getting bigger and moving in towards the glacier. So it could be connecting the ocean to the main part of the glacier here very quickly. And when you look along the sides, this is a little oblique photo close up where you can see this cliff. It's falling apart, and it's basically just dirty ice or dirt covered ice in those walls. So this entire strip of land appears to be, or at least the big parts of it, probably the center section for sure, is like old ice left over from maybe Little Ice Age or last glacial max that's in the ground, and it's covered with soil and vegetation, but it's highly susceptible to going away quickly. This is a series of outlines of these two little lakes, including the Lagoon of Doom here, that Mark Fonstock made from 22 years of Landsat imagery, and you can see how much they've grown during that time. So, and this is another little video clip just flying along the foreland, so you can get a little better idea of what it looks like. Another time lapse, so it's sped up quite a bit. And you can see all this thermokarst, the glacier ice over here on the left with debris on it, and then here's the Lagoon of Doom coming up on, marching its way into the glacier. And then you can see more and more vegetation out here, lots of trees, lots of bears. Then we come around over here to Malaspina Lake, which actually has been kind of stable over time. We don't think that that is going to be the major point of instability. So here's our radar coverage over 8 years using 4 different radars. Basically, the radar has always been secondary to the LiDAR in these campaigns. And so we kind of take what we can get. And if there's a day where there's good weather here and not so good everywhere else, then we might go fly some lines over Malaspina. And so gradually over the years, we've built up this grid, this kind of coverage. But it made interpretation, processing and interpretation a bit of a challenge, because this evolution of radars, there were years where there were issues and different timing things, and Michael and Brandon have worked out a lot of that stuff recently. So we have a complete uniform data set. Here's a comparison, just to give you a sense of how these different radars look. The UAF monopulse is actually probably in some ways the nicest, cleanest data, but it's a really difficult one to use operationally. It's got about 200 meters of stuff that you tow behind the plane. The pilot really did not like it. And then the JPL system, which looks a little blurry because the resolution wasn't super great. And then our 2.5 and 5 megahertz systems at the bottom, which I think are awesome. Definitely the 5, you can see higher bandwidth, higher frequency, higher bandwidth, higher resolution. But it's sometimes more susceptible to scattering from surface debris. So the 2.5 kind of seems like the old reliable right now. So a couple of profiles. This is just crisscross here on Malaspina. For the top one, going from the terminus down closer to the coast, up towards the mouth of the glacier up there at the top. Hit this big dip below sea level right near the coast. And then it comes in and it's relatively smooth and flat as the ice gets thicker. The east-west profile here, B2B prime, you can see big trough right here, kind of in the middle. And it's very asymmetrical. So I'll show you a map view of this, but also at this deep point here, the glacier, the deepest points get up to over 800 meters thick, which puts it well below sea level. So we'll go to the map views. This is the first off the gridded, just the flight lines, just the data along the flight lines. After Brandon did a lot of work to match up all the different radars. And so you can see on the bed elevation, there is a trough, that big trough I showed a profile through right over here, kind of over in this part of the glacier. There's a big deep area over here. And then of course this corresponds to ice thickness over on the right. But I'll go to his kriging results, which show bed elevation there on the left and ice thickness on the right. And bed elevation's going down to 450 meters below sea level. And this big trough coming down right down to basically the center here. And then a few other troughs, and then certainly this low area here, which is a pretty large basin with some troughs connecting it. And then the eastern side over here is a little bit higher and smoother relative to the rest. In terms of ice volume, we've got about 600 cubic kilometers of ice, which is equivalent to about 1.5 millimeters of sea level rise just in that glacier. So Malaspina, in terms of the geologic context, is pretty interesting because it sits in a very complicated area. You've got basically the Pacific plate is pushing the Yakutat microplate into North America. And it appears that there's about 14 millimeters per year of shortening accommodated beneath Malaspina, or it kind of needs to be to make this all work, all these geodesy measurements. So people have proposed that there is a continuation of offshore faults underneath Malaspina, but they didn't know where they were because nobody had any data underneath Malaspina. This is Brandon's compilation of proposed faults in this area, and it shows thrust faults on bounding Malaspina, which that's okay. That's pretty easy because you got the mountain ranges right here. That makes sense. But then this one coming up, the Malaspina, this Forlands fault coming, this thrust fault coming up underneath the glacier. If you put it on the topography, it actually matches up quite well with the this central trough. And so, and when you think back, to go back to that slide I showed with the big asymmetry of that trough, it could be explained by being fault controlled rather than just an erosional channel. And then the other interesting thing is these channels, like this one connects to this stream that is clearly putting a lot of sediment out into the ocean here with this plume that you can see in the imagery. And really all these streams are putting out plumes of sediment into the ocean. That's the biggest one. And then, so there could be subglacial hydrology, that's being partly fault controlled, but also then controlled by the ice, the distribution of ice itself, the ice thickness, basal topography. So that's an area of future investigation. And then the Laguna Doom is right over here, and it's very close to connecting like into this really deep area of Malaspina right there, right off the coast. So it does look like a critical zone. Over on the east, it's pretty different. And that's part of the reason why I say that the Malaspina Lake over here seems fairly stable. And things are a little smoother. You don't have these deep channels, and the elevation is closer to sea level over there. So, and so what we're trying to do is look at things like, this Cotton et al. Paper from 2014, where they were analyzing surface morphology. They didn't have any bed data, and the regional tectonics to say that there was probably a difference between the eastern and western part of Malaspina in terms of the subglacial geology that could be impacting the glacier itself. And they were looking at flow differences on the surface over here, where this eastern side, for some reason, surges, has had surges recently. So our hunch or hypothesis is, maybe it's more of a hunch, is that the bed conditions are controlling subglacial hydrology to a certain extent, which is then controlling ice flow. So it's a combination of the topography and the hydrology. We just got this new NSF grant to study Malaspina, and we're just getting started up. We haven't, this coming summer will be the first summer in the field. But the University of Alaska with Chris Larson, Martin Trufer, Mark Fonstock, and myself at University of Arizona, and Doug Brinkerhoff at University of Montana, who's the modeler on this. And we're going to be doing geophysics in Forlands, combination, probably mostly TEM, transient electromagnetics, basically whatever will work to assess the ice content and stability, and then geophysics on the glacier to assess the bed conditions to see, like, is it all sediment, is it crystalline bedrock, and also the debris thickness on the surface of the ice. And then additional radar to fill in gaps, and LiDAR flights, which will hopefully include the Forlands for change. And we actually did a Forlands survey this last summer we had a chance to get quite a few hours of mowing the lawn back and forth along the forelands doing LiDAR. So we've got kind of a base map to look for change, quantify change. And then all that's going to feed into this comprehensive modeling effort to try to predict what's going to happen with Malaspina and what are the scenarios in which it could catastrophically retreat, and what would that look like. So the forelands work is going to be interesting because we're going to be going to all these places that are a little difficult to get to. And there's sometimes dense vegetation, and then there's these big bears. There's a lot of bears. So there's a little, like a 10-second clip of cruising down the coast here at about 50 feet. And if you look close, you can see like at least 5 bears. So there's 2, and there's another one in the water here. And there's another one running there. And there's another one up here somewhere. That's a lot of bears. Oops. So we're gonna have to be prepared for that. So we're also, some of us within EDO, including Chris Herrig, Ali Garangi, and Lynn Carter, and myself, are talking about a new proposal for a large-scale campaign to measure accumulation. So, we're getting bed depths, glacier geometries, but in order to really do this right, we need to understand what the input side of it is. And so a couple of years ago, we did test the snow radar. Forgot to put it on here, but it's from University of Kansas. It's 2 to 8 gigahertz, very high frequency radar. It's only designed to measure last year's snow accumulation. So we flew it over these paths, including Upper Hubbard and this area I've been showing you examples from. So right in there. So here's one piece of that where you can measure the snow accumulation from the last winter up to almost 4 meters thick in places. So if we could get some repeat airborne campaigns going to do this in addition to the LiDAR, then that will enable a lot of new mass balance constraints. And then also we could link it to satellite observations, which are typically just not too great in these mountainous terrains. So, but we could help calibrate those. So that includes a bunch of different missions. So we're thinking that this would be a good large-scale NASA proposal, probably the Earth Ventures suborbital program. All right, so in summary, we're able to sound many Alaskan glaciers, especially in the terminal lobes where things are active and happening. There's lots of interactions. All the major glaciers that we've mapped exhibit these over-deepenings, beds well below sea level near the coast, and troughs and channels, troughs or channels, which all of this facilitates rapid retreat and collapse. The new work that we're going to do on Malaspina Glacier will help us model the whole system and predict possible catastrophic retreat scenarios. And then if we can get this done, regional accumulation measurements would really help close the loop for mass balance and leverage satellite observations. So I think we're starting to get to where we can answer the question of how these Alaskan glaciers work. Why, exactly what are the drivers and controls for their rapid change, and what they're going to do in the future. And then hopefully that will help us understand glaciers worldwide that are starting to change as well. So anyway, it's pretty exciting. I think it's fun to work there. So thanks a lot, and I'd be happy to take any questions.
All right, thank you, Jack. We have time for some questions. You can either type your questions in the chat or raise your hand with the raise hand feature, and you can ask Jack your question yourself.
I have a question.
Go for it.
So Jack, that's really cool. I just wonder with those over deepened areas, and I get the concept of the fault control along the axis of the Malaspina. I guess there's a couple of zones of that, but it seemed like there are a couple of really deep divots along there. that extend, I don't know, a couple hundred meters below the general slope of that over deepened area. Yeah, those purple areas. And is that just super erodible stuff that it's carving through that's causing that, or why do you have features like that?
No, I wish I knew the answer to that question. I think when we do some seismic work, we'll get a better handle on what's down there. It is very likely easily erodible. You know, the whole history of glaciation along there, just massive amounts of erosion as those mountains are uplifted. And so most likely it's all sediments. I'd be surprised if there's any kind of crystalline bedrock exposed underneath the glacier anywhere. So, and then also during previous retreats where, you know, the glacier was back and sea level was higher, these could be, you know, this could be erosional channels from then left over. So I'm not really sure. But,
okay, we have a question from Joellen in the chat, and I think many of us share this question. How are you going to manage the bear problem? But I guess more broadly, I just wanted to ask you also, what is the most challenging aspect of fieldwork for you, apart from the bear problem?
Well, to answer the first part, I haven't done a whole lot of work on the ground in Alaska. It's mostly been flying around. But, you know, typically people take bear spray and guns. Like you use the bear spray first, and then you have a gun as a backup just in case it doesn't work. And there are definitely cases where it doesn't work.
It better be big.
Yeah. No, like, and several people were killed a couple of years ago by black bears, which is a little unusual up there. And there was a geologist and a field assistant doing some work, and they only had bear spray, and one of them got killed. The other one escaped. So, and I think, you know, just having multiple people together helps a lot. So, I think the most challenging thing is the weather. It's you can just be battling that for, you know, a week or two before you get a good window, and then you get a good window and you just go all out and do as much as you possibly can. But we're trying to hit such a huge, in general, aside from the Malaspina study, we're trying to, you know, the field area is so big that you know, you're just trying to get anywhere, and sometimes it's bad everywhere. Or you've gone down Southeast Alaska and then it gets good up in the Alaska range and you're just too far away or something. And then sometimes it looks great and then the winds are too strong and you're just getting your butt kicked too badly to stay up there doing it. So yeah, it's the weather.
Thanks. Pete has a question. Go for it, Pete.
Hi, Jack. Thanks a lot for that talk. Really great stuff. Brought back a lot of memories when I was working over in the St. Elias range some decades ago now, I guess. But, you know, one thing I've always been interested in the Malaspina Glacier, especially, is the pattern of folding that you see on the eastern side of it. Do you know anything about that? I mean, what is going on there? Are those just very shallowly plunging folds, or is it?
They seem to be moraines that are being folded as it flows and it compresses. Actually, I've got Brandon had a cool video in his talk. If he doesn't mind, I could show that. It's pretty cool. It's just like a series of Landsat images. If I can switch which screen I'm sharing. So this is time lapse. You guys see that now?
Yeah, that's beautiful.
Wow.
Yeah, isn't that amazing? It's
Wow.
it's just cruising out and deforming. So presumably, you know, those all started out as lateral moraines that were straight, and then they got folded. If you see kind of up in the upper right where they start getting folded, and then that propagates down the glacier. So you could potentially unravel that, you know, like back it out and get at the deformation history from that.
Wow.
It's about, there's 1 minute left. So let's stop right here, but Jack is going to stay on for the class discussion with Marcus and Paul after this. So save your questions for there. Everyone's welcome to that.